Okay, so last time we just talked about homogeneous equation. We talk about homogeneous functions. That means essentially all the terms of the function have the same power when the function has two or more variables. That's homogeneous function. And then if the differential equation has homogeneous functions for those m and n in the equation, and then the equation itself is called homogeneous. Okay. For homogeneous equations, we can use substitution of y equal to x times u, or x equals y times b, and then convert the original differential equation into a new equation that we can solve. So that's the first case of solutions by substitution of this section. And there's some other situations that we can also use substitution. The second case or second situation is called Bernoulli's equation. Okay, so Bernoulli's equation is the form of dy over dx plus p of x times y equal to f of x times y to the n. So it is not a linear. You have the nth power for y. But for these types of equation, we can still use substitution to solve the differential equation. And in here, n can be any real number. It's not just the integers. It can be decimals or fractions, or even irrational numbers. So this is a special type of equation that can be solved by substitution. All right. So it turns out that if you let u equals y to the 1 minus n, then you can convert this equation to a new equation and solve it. So then we just introduce a new function u equals y to the 1 minus n, as I said, and then you just follow the procedure for substitution. You have to write down du in terms of y and dy. So if you do that, what you get is the 1 minus n times y to the negative n dy. That's du. So that dy will be 1 over 1 minus n times y to the n if you divide by 1 minus n and multiply y to the n. And then dy over dx obviously will be 1 over 1 minus n y to the n times d over dx. And remember, y equals u to the 1 over 1 minus n. If you rewrite u equals y to the 1 minus n, you just take the 1 minus nth root on both sides to get a y. And then plug that for y. So then you get dy over dx equals 1 over 1 minus n times u to the 1 over 1 to the n to the n times du dx. So at the end, you get dy over dx equals 1 over 1 minus n u to the n over 1 minus n du dx. So that's a little tedious, but you just use the rules of the powers. All right. So that's the general guideline to solve this Bernoulli's equation. when we do the examples, you don't have to use this formula as we just derived. But you just follow the same procedure. So let's just look at one example of Bernoulli's equation. We want to solve the equation of dy over dx minus y equal to e to the x times y squared. Okay. So this is Bernoulli's equation with n equal to 2 if you compare this example with the standard Bernoulli's equation. And the function p of x is just -1, and f of x equal to e to the x. Okay. That's the comparison of the problem with the Bernoulli's equation in general form. So as I said, we're going to use substitution u equal to y to the 1 minus n. So that will be y to the 1 minus 2 because n equal to 2, or y to -1. Okay. So then we just find out, what the new equation in terms of u. So y will be equal to u to the -1. Okay. If you rewrite this u equal to y to -1, you can easily, you can use the formula we had before, y equal to u to the 1 over 1 minus n, and plug in 2 for n, you get u to -1. But you can also get it from the equation of u equals y to -1 if you multiply y and divide by u on both sides. And then dy over dx is just 1 over 1 minus 2 u to the 2 over 1 minus 2 du over dx. So that's the formula we got. So that's negative u to the -2 du dx. Or you just start from y equal to u to the -1 and take the derivative with respect to x on both sides. So then we got dy over dx reading in terms of u and du over dx. And we can, write down everything in terms of u in the new equation. Okay, so the original equation dy over dx minus y equal to e to the x times y squared on the left. The first term dy over dx will be negative u to the -2 du over dx as we got. The second term is y or u to -1. So that will be minus u to -1 equals e to the x times u squared, y squared, which is just the u to -1 squared. So that will be u to -2. All right. So then what you do is just multiply u squared on both sides and get rid of this u to the -2 and u to -1 in the equation. And then multiply -1, to the equation on both sides. At the end, you're going to get du over dx plus u equals negative e to the x. Remember, u to the 2 times u to the -2 is just 1. And u to the -1 times u to the 2, or u squared, you just add exponents, -1 plus 2 is just 1. So you get u to the 1, or u. Okay. So that's the new equation with u and x, and we know this is a linear differential equation. We can solve it by using the integrating factor. So if you still remember the formula for integrating factor, you just compare this first order linear differential equation with the standard form, and then you recognize p of x is just equal to 1. and f of x equal to negative e to the x if you compare the standard form of du over dx plus px times u equal to f of x. So the integrating factor mu is just the e to the integral of p, but p is just 1, so you get the x if you integrate it. So the integrating factor is just e to the x. And then using the integrating factor, we can find out the solution to the differential equation, the new differential equation, which is u equal to integral mu times f plus c over mu. Now mu is e to the x and f is negative e to the x. So plug in. Okay, let's see. E to the x. Let's see. Did we get everything right? I think I made a mistake in here. E to the x times negative e to the x should be e to the 2x, negative e to 2x instead of negative 1. So there is an error in here. But that's easy to integrate. So if you integrate negative e to the 2x, you should get negative half e to the 2x. So the top will be negative half e to the 2x plus c instead of negative x plus c. And then you divide by e to the x. Okay. And then to find y, you just flip it. Y is the u to the negative 1. So that's 1 over u. So you just flip the whole thing. So the final answer should be y equal to e to the x over negative half e to the 2x plus c instead of negative x in the denominator. I'm sorry for the error in here. Any mistake? Any questions?
Yeah, I have a question.
Yeah.
Why did e to the x minus or times negative e to the x equal negative 1?
Yeah, as I say, the e to the x times negative e to the x should be negative e to the 2x. That's an error in here.
Okay.
So, yeah. So we need to correct that. Any other questions? So that's the Bernoulli's equation. Another example that we can use substitution to solve a differential equation. So that's a special type of equations that we can solve by substitution. And there is another situation that we can also use substitution to solve the differential equation. If you don't have any questions. Okay, so that's called a reduction to separation of variables. Okay, what it means is, you have an equation of dy over dx equal to f of ax plus by plus c. So the function f on the right hand side is a function of ax plus by plus c instead of x or y. So this is also a special type of equations that we can solve by substitution. What you do, you just simply let u equal to ax plus by plus c, and then plug in that into the original equation and solve it. Okay, so you can easily obtain du over dx. The derivative of u equals a plus b times dy over dx over prime. the derivative of constant C is just the 0. So A, B, and C are just the numbers or constants in this case. So you can easily solve dy over dx from this equation to get 1 over b times d over dx minus a. And then you plug that into the original equation, so you're going to obtain a new equation for u and x and solve it easily. So we'll see one example in here. So in this problem, we need to solve dy over dx equals negative 2x plus y squared minus 7. So again, this is not a linear equation, but we can, use substitution to solve it. So we're going to let u equal to negative 2x plus y. Okay. So this is the thing squared in the original problem. All right. So take the derivative on both sides with respect to x. We get a d over dx equal to negative 2 plus dy over dx. Move 2 to the left-hand side, we get dy over dx equals du over dx plus 2. So then we can rewrite the original equation as du of dx plus 2 equals u squared minus 7 if you plug in dy of dx by du of dx plus 2 and negative 2x plus y by u. So now it will become a separate equation that can be solved. So subtract 2 on both sides, you get du of dx equal to u squared minus 9. And then rewrite the equation as du over u squared minus 9 equal to dx. Integrate on both sides. Okay. So once again, we got u squared minus 9 in the denominator that we can factor as u minus 3 and u plus 3. And we can use decomposition of fractions or partial fraction decomposition, if you remember it. Last time what we did. So you can rewrite 1 over u minus 3 times u plus 3 as 1 over 6 times 1 over u minus 3 minus 1 over u plus 3. Okay. So you can rewrite this fraction in terms of the factors, and it becomes a sum or difference. Okay. So then you can integrate easily on both sides. So what you get is 1 over 6 natural log of absolute u minus 3 minus natural log of absolute u plus 3 equal to x plus some arbitrary constant. We use C1 to denote it. So we can simplify this solution or equation and to get 1 over 6 times the natural log of absolute u minus 3 over u plus 3. Remember the difference of 2 logarithm with the same base becomes logarithm of the quotient of the two things. So that's the left-hand side. So then what? Then u minus 3 over u plus 3 with the opposite sign equals 6 times x plus 6 times c1. So again, this table here and the left side should be natural log of absolute u minus 3 over u plus 3. Okay, I just forget that to put that. And then you take the exponential on both sides, you're going to get the u minus 3 over u plus 3 times some constant C2 times e to the 6x This C2 comes from e to the 6 C1, but it already takes care of the plus and minus sign. That's why we don't need the absolute sign again in here. If we allow C2 to be both positive and negative. All right. So then, remember, U is negative 2x plus y, so plug in negative 2x plus y for U in this equation. And then we got negative 2x plus y minus 3 over negative 2x plus y plus 3 equals C2 times C to 6x. Remember, we have to, solve for y. So we still need to plug in back y in here. All right. So then you do a little more algebra, multiply negative 2x plus y plus 3 on both sides to get the negative 2x plus y minus 3 equals negative 2x plus y plus 3 times C2 times e to the 6x. And you can, do more simple algebra, distribute C2 e to the x to each term on the right side, and then combine like terms. So move in the terms of y to the left and the other terms to the right, so that we can solve for y. Okay, so I'm not going to go through all these details. You can check it easily by yourself. So at the end, you can factor y from the left-hand side and solve the whole equation and get a solution to be y equal to 2x minus 2 times C2x e to the 6x plus 3 C2 e to the 6x plus 3 over 1 minus C2 e to the 6x. And you can do a little simplification and rewrite this solution as 2x plus 3 times 1 plus C2 e to the 6x over 1 minus C2 e to the 6x on the right-hand side. So that's the solution to the problem. All right. So it did take a little tedious work to solve it. Even the substitution is straightforward. To actually solve the problem requires a little more steps. Any questions for this example? So let me just stop here if you have any questions. I'm going to stop the recording.